Welcome everyone to today's Explainer. I'm absolutely thrilled to get into this one with you because we're looking at something that represents a massive, profound shift. And I'm not just talking about a shift in how we understand biology, but in the fundamental evolution of artificial intelligence itself. Today, we're exploring a breakthrough called AlphaGenome, and we'll see exactly how it acts as a bridge toward an entirely new conceptual framework called the energetic paradigm. Let's jump right in. To set the stage, let's ask ourselves a pretty massive question. What actually happens when we alter the code of life? For the longest time, we thought the Human Genome Project was kind of the finish line. We assumed that just reading the DNA sequence would give us the ultimate source code, the complete instruction manual, but we quickly realized a pretty hard truth. Simply reading the code didn't actually explain how biological systems change and adapt under pressure. Just recognizing a sequence, well, that is definitely not the same as understanding a living, breathing system. Okay, let's dive into this. Here is the highly structured cognitive journey we're taking today. 1. The genomic dark matter. 2. How AlphaGenome changes biology. 3. Patterns versus state transitions. 4. The energetic paradigm. 5. Building large energy models. And 6. The future of AI for science. Starting with Section 1, the genomic dark matter. It's time to move beyond the source code of life. Notice the absolute massive disparity here. Look at that tiny slice. That represents our protein-coding DNA. It's just a tiny fraction of the whole genome. The vast majority of our genomic variation actually happens in that massive slice, the non-coding regulatory DNA. For years, people colloquially called this junk DNA or dark matter, kind of implying it was just inactive filler. But no way, it is entirely the opposite. It actually acts as a highly complex distributed control architecture. So why does this matter? Well, think about it. A cell can't possibly activate every biological process at maximum intensity all at once. That would be literal chaos. Regulatory DNA, this so-called dark matter, is essentially the management system. It allocates our highly limited material, metabolic capacity, and time among competing functions in the cell. It determines where biological work is actually performed across the whole 3D structure of the genome. And honestly, just as importantly, it determines which alternative pathways get suppressed. Which brings us to Section 2. How AlphaGenome changes biology, moving from simple sequence to systemic consequence. AlphaGenome doesn't just read the code, it maps what happens when you actually poke the system. Tracing this left to right, Step 1. You have a DNA sequence perturbation, like a single base mutation. AlphaGenome tracks how that one tiny local tweak cascades into Step 2, changes in chromatin accessibility, transcription factor binding, and RNA processing. And finally, it maps all of that to Step 3, a functional state change and a real biological consequence. It literally connects the local tweak to the distributed result. And this brilliantly illustrates why AlphaGenome is such a monumental leap forward. It combines these 4 distinct capabilities. It uses long context windows because regulatory relationships can span massive, complex, 3-dimensional genomic interactions. It offers unified prediction of multiple molecular activities at the same time. It works at an incredibly high base-level resolution, and absolutely most crucially, it estimates effects by directly comparing altered sequences with unaltered ones. Basically, it asks, what happens if I change this one specific thing? Let's pivot to Section 3. Patterns versus state transitions. This is the profound shift in AI architecture. Think about it like this. Traditional AI is basically the world's most advanced autocorrect. It predicts patterns. It excels at symbolic continuation, guessing the next word or the next pixel based on statistical likelihood. But AlphaGenome is an entirely different beast. It acts way more like a flight simulator. It models the relationships between perturbations and structured biological states. It maps how pulling a specific lever or mutating a specific gene changes the physics of the entire system, showing us exactly which biological states remain possible and which become completely inaccessible. The math here perfectly captures this shift, and I promise it's straightforward. The top row is standard prediction, a function of a sequence, and its context gives you an outcome, y. It's static, right? But look right below that at variant analysis. We're looking for delta y, the difference between the system with a tiny intervention, delta s, and the completely unaltered system. This isn't just describing a static system, it is modeling an actual transition. It calculates exactly how the biological system reorganizes itself under a real intervention. Moving to Section 4, the energetic paradigm, a universal framework for structured transformations. So, the crucial point here is that the energetic paradigm treats real intelligence as the capacity to represent and control structured transitions under conditions of scarcity, constraints, and competing objectives. True intelligence isn't just spitting out what is statistically likely, it's determining what transitions are physically possible, what they're going to cost, and whether they're reversible. The energetic paradigm uses this really elegant representation. A system S is defined by its current state, X, its energetic or operational capacity, E, its constraints, C, its feasible actions, A, and its transition dynamics, T. Now, to be clear, AlphaGenome isn't a full, complete energetic paradigm model just yet, but it does a brilliant job approximating T, the transition dynamics. It predicts exactly how a biological state transitions when an action, like a sequence mutation, is introduced. Let me read this quote from the source material because it really hits the nail on the head. Intelligence becomes more useful when it can preserve the connection between a local change and the downstream reorganization of the larger system. Having a long context window in an AI model isn't just about giving it a bigger memory buffer. No, it is a structural requirement. It's required to actually track those indirect domino effect causal chains running through a complex system. On to Section 5. Building large energy models, and importantly, what AlphaGenome still lacks. To be a true large energy model, or LEM, a system needs things that prediction alone literally cannot provide. It needs an explicit objective function, like what is the system actually trying to achieve or preserve. It needs viability and stability criteria, so it knows if an intervention might accidentally crash the whole system. Right now, it lacks an active control loop to observe, correct, and optimize its own interventions in real time. It doesn't quite have full multi-scale integration yet. And of course, it currently lacks representation of institutional and ethical constraints, which are absolutely critical when we start managing real-world interventions. Let's see how this builds into the 5 layers of a true biological large energy model. To genuinely evaluate candidate transitions, an LEM would have to integrate all of this. From the lowest baseline level of genomic control and molecular operations, scaling all the way up through cellular states into tissue and organism dynamics, and finally, being contextualized by external environmental conditions. You basically have to capture the entire hierarchy of causation. Finally, Section 6, the future of AI for science, moving from predicting representations to governing transitions. Take a look at this exact evolutionary path for AI as mapped out in the source. We started way back at stage 1, sequence recognition, literally just identifying patterns. AlphaGenome proudly occupies stage 2 right now, state transition modeling. But the future? That is pointing us straight towards stage 3, constraint-aware evaluation, and ultimately stage 4, controlled system intervention. We are fundamentally moving from just reading the world to understanding how it shifts to safely and actively guiding those shifts. Don't let the math here intimidate you. The logic is beautifully straightforward. This represents the ultimate objective of a large energy model. It simply says that the value of an action or intervention is equal to its expected benefit, minus the required resources, minus the risk of system instability, and minus the cost of irreversibility. Makes sense, right? Future intelligence is entirely going to be about the disciplined selection of transitions that balance benefits against costs and risks in the real world. The source text sums this whole thing up with a massive, paradigm-defining statement. The future of AI is not predicting representations, it's governing transitions. Making a model larger by just feeding it more data doesn't automatically make it deeper or smarter. It only becomes deeper if it actually respects the constrained physical structure of reality. We have to move beyond just generating plausible descriptions and move toward true structured intelligence. Which leaves us with this final, thrilling question to ponder. Are we ready? Are we ready to move from simply predicting the world to actively and safely governing its transformations? AlphaGenome has absolutely shown us the door to the energetic paradigm. Now it's really up to us to walk through it. Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you next time.